Hold on, guys. Let me start my slides. Where is it? So, welcome to today's talk, which is an introduction to P2PRC by me, Akhilan Sivakumar. So, an introduction to this project. Well, P2PRC is just a simple peer-to-peer network that provides the possibilities to run any sort of task or computation across a set of nodes. There would be simple explanation to it. So, what are the core features? One is detecting other servers by hopping through servers in the network. Just means that you have your machine running. You might have information on one server. You can go to that server, download its IP table, which consists of information of other servers. And by doing this process, you are traversing through the network. And at a point of time, you have your own list of a set of servers you know. And then with those set of servers, you can probably run certain tasks through them. So that comes to my second point, which is creating containers and removing containers in a single command. Yes, so once you know information about a server, like through the server's IP address, you can start a container and then SSH inside the container and start running tasks. To do this, we mostly use Docker. So because we are using Docker, if the machine has access to a GPU or has a GPU, if a server has a GPU, we can basically do a GPU pass through to the Docker container itself. So from the container, we can access the machine's GPUs to run some sort of heavy computation as such. I think the most important point of all of this is that all of this is a single binary file. Okay, there are dependencies like Docker and Ansible we use, which are not part of it, but the rest of the implementation is just one binary file. And this is very important because if, for example, we can just distribute the binary across a set of machines and we don't need a Go compiler to run them every single time. So the challenges this project is solving, one thing is prioritizing IPv6 addresses over IPv4 addresses. So if you live in the UAE, or most of us in the UAE have an IPv6 address. This means that we don't have to worry about problems such as NAT, and we all have our nice little public address. And most of us do have it, but we don't realize it. So this means that what this network does is, as a user of a server, you can specify if you want to use your IPv4 address or use your IPv6 address. And as you can force it. So by default, using an IPv6 address has an advantage because you don't have to do change any settings in your router, and then directly anybody from the outside can connect to your machines and start creating containers, closing containers, and so forth. The second one would be using nodes close by. This means that because it's a peer-to-peer network, we do provide metrics such as latency for all the servers, and this would force a user by default to use a server with lesser latency, especially if they're doing something like live renders, and this is what we're doing in the point of view. The third point is learning network to traversing. We talked in the previous slide that by knowing information about servers, we can download its IP table, which consists of information of other servers in the network. And by doing this, we are traversing through the network. And the fourth point is a lighter version of container orchestration. So technically you can think of this project as a lighter version of Kubernetes, but more focused for peer-to-peer networks. So this means that when you're using this, if you're a person who uses CLI applications commonly, there's almost no learning curve, and it's pretty straightforward to use and set up. Nothing much to learn about. The fifth point is, this is kind of important for us, focusing on instructions to execute rather than the virtualization itself. So nowadays, if you look at a Docker file, most Docker files are built with some certain dependencies to install and do certain tasks. And then that's run inside some Ubuntu image, all at the Docker file itself. So this is all done at setup. But what we want to do rather is kind of something different. We just want maybe the Docker or the Qmenu virtualization just to run a base image of an operating system, for example, Ubuntu. And then we want to use something like Ansible or some sort of plugin system where once the virtualization system is set, or once we can SSH that machine, we just SSH into that machine, and then we install our dependencies. And using this approach, we are not specific to the virtualization. Like what we run can run on any sort of virtualization, any machine, so long as you can SSH inside it. Makes a much better generalized approach to think of it. In simple words, I would like to quote it like this. It's a friendly way to execute tasks on your friend's machine and an alternative to cloud providers. Let's go with a live demo, I think, to showcase what this does. So to install this thing, it's as simple. To install this, you just have to do make install and something straightforward, but I'm not going to do it now because it does take a while to do it. But I already have it installed. You can look at in the end, I'll provide the link to the GitHub repository. From there, you can look at the install instructions to see how to set it up on your computer. So the first thing we want to do is P2PRC-H. Sorry, my bad. This shows that everything is installed on our machine. So the first thing, let me just reset. Okay. So, second. Okay. If I do cat config.json, so this is our configuration file we have here. This will point it to our default Docker container we want to run. This is another point. This points also the path where all the Docker containers are present for this project P2PRC, path to our IP tables. If you have an IPv6 address, we can provide it here. We'll show how to get that. This is the path to a plugin, this is still under development, but this is something kind of useful. We will try to make it available in future builds or future releases. This is the port if you want to run as a server, what port should it be on? And probably the path to the speed test files. We haven't enabled this feature yet. Basically, this is for getting a download and upload speeds and so forth. And this would be the path to track containers you created, and we'll see more about this later. So the first thing is our IPv6 address field is empty, and how do we get this IPv6 address? Well, it's pretty simple. You can just have to do P2PRC -- use the flag called NI, which stands for network interface. If you do enter, you can see you have a bunch of information about your network interfaces available in your machine. As you can see here, I already have an IPv6 address at this, so I just have to copy this right here. I can go to my config file, and I can just add it over here because this is my current IPv6 address. So, and the next feature is now we have a new machine, and if I do the command P2PRC --ls, we know this is our machine, which is not running as a server. So, of course, this latency is 0 milliseconds, or it's actually not running as a server, so it's just there for our information. But this is a server we know by default. This is part of the repository. If you go to the website, P2PRC, you can see information about server information over here, and we know about this server currently, if I'm not wrong, which is it. So this server what we know is the server might know more information about other servers in the network also. So what we can do for that is we can update it. So we can do P2PRC --us. This takes some time to run, but what this does is it goes to the other server, pulls its IP tables, sees the IP table information on that server, and then appropriately does a small traversal. Because now we have a small network, it should take relatively less time, but it does take some time. You can think of it like a brute force approach, so it's not the most efficient way to do it, but it does the trick for us, I guess. Just give it some time. Apologies, it does take some time to run. But anyway, till it runs, I can explain. This is the website over here, p2prc.keynote.io. We have the GitHub link, the Discord server, and so forth. So if you're interested on the project, the best place to get started is here. Okay, so it's perfect. We have ran it. As you can see, we have downloaded more information about servers in the network. As you can see over here, we got latencies, which is important to see how close they are. This is a closer network because this server is in India, which is not too far away, but whereas these are in the EU, which is relatively far away. So now we know server information. What we can do with it now is we can, for example, let's take the closer server IP address, and if I do P2PRC --specs, and I paste the IP address, you can see I know information about my server, about the other server, which is this 32 core processor. I have about 970, I have like a 1 gigabyte RAM, 24 gigs of storage, and so forth. This is for now for the test network. Most of them are on cloud servers, but It can be on any machine so long as it escapes NAT or you have an IPv6 address at the current implementation. So one command. So we know about the server. Let's say how do we create a container so we can access it and do our operations? So for that's easy. P2PRC -touch would be the command, and I can just paste the IP address over here. And that's it. This is all we need to do to create a container. I will just take some time because it's Docker. Let's give it some time. What did I give? Provision. Actually, this might take some time to create because I've not built it before. Let me try with a smaller server here, where it might be much quicker to build the container. This should be relative. No, it's not this one. I didn't copy paste it correctly. My bad. Okay, there we go. We got one that spins up relatively quicker. So what we have here is our SSH username, password, ID, blah, blah information. As you can see here is we can access the machine via this way, which is we have an SSH access with port 22, our external SSH port, and so forth. So how do we SSH? SSH master at, we know this is the IP address of that machine. Right here, we know the port number of our external SSH port number is this one right here. And by doing this, you can just say yes and password, and yes, you're in the machine right there. This is the easiest way to access the machine. So let's exit this machine anyway. So get back. So we've created a container. How do we track all the containers we created? So we can just do P2PRC --tc, which is to track containers. As you can see, we've created one over here, so we know information about this container right here. So before learning how to remove, there's also something else which is important. So now we're limited to one port right here. This could be an issue in a way, because sometimes you would want to open more TCP ports to run a web server, or you want to create like your own little connection, but maybe it could be using a specific port number or another port number. You just want multiple ports to be open for multiple operations. To do that, you can just use a tag called p-b and specify the number of ports you want to open. Let's say I'm going to open 3 extra TCP ports. So as you can see, instantly we've created another server that will create another Docker container, and then we have our 3 auto-generated ports. In a future release, you can also specify the port number you want to create and whether it's a TCP or UDP port. But currently, we only auto-generate TCP ports at the moment. So if I do this command, we can see that we've created 2 containers. It's because for now, all the print functions go through. We have like one function that just prints everything as a JSON output for simplicity. It's debatable if you want to switch that or not, but I guess for now this does the trick. What we can do right now is we want to remove these containers we created. Let's assume we've done some operations inside them. That's pretty easy. We just need to know 2 things. One is the ID number so the Docker ID number right here. So that would be P2PRC --rm --ID. I'm just going to capital them in, but for the RM, I'm going to, because I know it's in this, both my containers are on the same machine, so I know this is the IP address to that. Doing this should not take that long, should be relatively quick. Let's give it some time. Yes, so doing this, if I do P2PRC --track containers, TI, I think it's TC, you can see that we have removed one of them. So let's remove the other port. We removed one of the containers, let's remove the other one also right now. So copy that. I should just change the ID. And anytime soon, let's give it some time. And we have removed also the other container, which is great, which is what we wanted to do. So we know how to create, remove containers, view the specifications of containers. Let's see what else am I missing to showcase. So the GPU flag, because at the current moment I've not started, I don't have machines yet in the network which have GPU specifically for this current demo, for today's demo. So we couldn't use this flag, but you could do something like here, and then you could just say dash GPU. And what this will do is lets the GPU pass through on the server side, which has a GPU. And of course, at the current moment, we only support NVIDIA GPUs. So this flag is useful if you have an NVIDIA GPU. We showed NI. Okay, so this is still in build, but I can show what this flag does. If I do the flag dash VP, this will show like a bunch of plugins we have. So you could do something like P2PRC, an IP address of a server, create the container and run the plugin Minecraft. And that could just, for example, create a Minecraft server on the other machine, or even create Minecraft and do a WebRTC stream straight to your machine so you can kind of play Minecraft, but it's rendering on another machine. This could be a useful use case for like plugins who are still under implementation as usual. So of course, another important thing is dash VI. Of course, I have to put, I think I need to put, okay, so I know why. I need to put the IP address of the server. I will get that from, okay, forgot where is it. LS, we'll choose this server right here for now. This shows all the current containers available in the server to execute. Horvath is for running TensorFlow distributed. Towards the end, I can talk more about this. But yes, you can basically, for this, you just can do something like P2PRC --touch with the IP address, --cn container name, and then if I just say run this guy, sorry, this will kind of just create, you can specifically, so server can have multiple type of Docker images also, even though we don't want this. But for now we can, and then you can run specifically that image by just providing the image name in as a flag. You can provide like container name as a flag, and then the image name. Let's see if I'm missing anything else. P2PRC --h. Port value, list servers. We talked about all the following. We should track containers, view plugins. I think we've shown most of the important features, so it's a good thing from our side. So let's get back to the PowerPoint to understand a little bit of how this works in depth. So let me go to view, Control F5, and here. So the implementation of this, how does the project work? Currently, these are all the following, we'll call modules or packages that come inside that single binary file, which we use for executing, or which we use as a CLI. So we have, yes, the peer-to-peer modules, client server module, and plugin module, which we're still building, which currently uses Ansible, but we want to write our own version of it in a way. So the peer-to-peer module, we have simple functions. One is read IP table, which is, as we showed in the CLI, of listing all the servers. We can read those lists of servers, we can write to them, we can print them out, of course. And then we have a speed test modules, which do kind of three important things. One is the latency. The second one would be the download and upload speeds. We have to disable the downloads and upload speeds. This is because they take a while to run, and we are planning the future implementation or future build would have them running as a background process. And this is, they interact with the client or server. So this means the client/server means kind of the local machine, because your local machine can act as a server also technically. So it acts with kind of three parties: a client, the IP table, and a server, to think of it. So this is what it looks like. This is the JSON file of how it looks, the IP table looks like, and this, as we saw previously, how it prints out. We have the client module overview. This is kind of important. This is mostly, so we have actually, we're not talked about it a bit in today's talk, but we have a CLI module, which kind of calls functions from the client module. So when you call a function called server specification, based on the IP address you put, it goes to the server, retrieves the server specification information, which is a JSON file, which is converted to a struct, and then that struct is printed, which outputs the information of this or the specifications of the server. We have the IP table. This is mainly where it works. Probably the next slide will talk more about this. So for example, when you run the flag --us, it goes, so that's called US means, wait, actually, is it? Oh, yes, it's --us, which means update server list, and it goes, traverses the network, and tries to get more information about servers inside the network. This is that function. Stop and remove containers. Of course, as you saw, the CLI module talks to the client module to start containers on various servers and remove containers on various servers. And we also have the --ls, which lists the IP tables in our current machine, and of course printing outputs, which is a single function for all the structs we have implemented. So let's talk about traversing the network. So this is like a simple diagram explaining how it works. So we have client node over here. We connect to the server we know about. And then what we do is we download the server IP table information, which you can consider like a merge, like if you do a git merge. So we merge, so if there's duplicate IP addresses, that's not added. So we just have unique IP addresses of different servers. And then what we do is based on those new servers, we use those new server IP addresses, go to them and download their IP address, their IP tables, and then we merge them. And then we do them so forth. To ensure they don't infinitely run or they don't take too long to run, we run the loop for 3 iterations, or we like to call them 3 hops in a way. So currently it's hard-coded to 3, but maybe we might do a few changes where you can set that number of iterations on your configuration file, which could be useful if you want to learn a network relatively quicker. And we have the server module, which is also important for us. You get to know about server information, so you know about the CPU information, the RAM information, so forth, and GPU. Currently, as mentioned before, we use NVIDIA SMI command, and we use a flag I think called --XML, which returns the NVIDIA GPU information as in an XML format. We kind of parse that XML format, we append them to the struct, and then we output them as server spec information. We have the upload/download route in our server. So our server is built completely using Gin for now. So it's just simple REST API calls, to say the least. This is disabled, but this gives information like the upload and download speed to that server. So we have like a peer-to-peer version of speed tests. This function is, so what this function does is, for example, we're updating an IP table. So first it checks if the client itself is also acting as a server. So while we are giving our IP table to the client, if the client is acting as a server, we also use its IP table, and we both kind of do merges on both our sides. So we both have, so end of the day, even if a server is down, if a server is randomly down, at a point of time, eventually the entire network is aware of it and they all remove them from each other's IP tables. That implementation is technically done in both the client and server side. So this is also one function. So if the client is at a server, this function also updates its IP table saying, oh, I found another server in the network. And of course, we have the create and remove Docker containers. These are more like interfaces, or we're planning to build them more like interfaces, but currently we've only linked them to a Docker API. So as you saw, when you did the command called --touch, immediately spins up a Docker container on the other machine. And this is just a server module as an overview. We can talk about now about the plugin module, which is something we are building on. So we can use Ansibles to execute instructions on different servers or different machines, whichever we want, whichever we've created our little containers in. So to think of this, I would say, okay, so first of all, let's just answer what are Ansibles. Ansibles are just a declarative way of executing. So it's a YAML file, which is a set of instructions, and then you can set like something called a host file with a bunch of IP addresses, and then there's SSH credentials. And then when you run Ansibles, it automatically runs those declarative instructions in each of those servers you specified in the host file. So we use Ansibles, but what we do in our implementation is we actually automatically overwrite the host file. So what you need to do is you just need this maybe site.yaml file, which consists of the instructions you want to execute on the other machine. But then we automatically populate the host file. So you don't have to worry about. So probably what you need to do is just say, I want to run ID 1, ID 2, ID 3, and automatically it runs as Ansibles on those servers and runs the tasks you need to run. And of course, you can have n number of possible plugins. So you can say run Minecraft, maybe run Modern Warfare, and then have your own gaming servers, host websites, run some TensorFlow benchmarks, whatever being up to you. So that this is our plugin module as an overview. And yes, this is what Ansible looks like in a way, like I said, declarative way. So you have task name, then the Ansible task. This could be an apt install, anything you like. You can also run shell scripts inside this, which is also very cool. And this is what our host file looks like. The Ansible port, this is just your SSH port, which we got over there. And do remember, all these are automatically populated, so you wouldn't have to worry about them. And the only requirement being Ansible, and Ansible has to be installed on your machine. But so currently what we are also trying to do is write our own version of this so that everything is part of the binary file, and you don't need Ansible as another dependency when running it. So this is something I did want to show. Something we are working on is a peer-to-peer version of Stadia. So Stadia, for those who don't know what Stadia is, it's kind of a recent company which Google has been betting on a lot. It's a cloud gaming service. So if you have a machine where you cannot run any powerful game, like let's say, what was the game I was talking? Oh yeah, like Cyberpunk, GTA 5, or anything. Basically, the game converter on the server provides a video feed to your machine with pretty low latency, very high frame rate, and you can even go up to 4K if I'm not wrong. And then your keyboard inputs are directly connected to the server, and then so it gives you the impression you're playing the game on your machine, but in reality you're playing on the server, and then you have no bottlenecks in terms of computation required for a game. And this is kind of our implementation on the side of what we built. This is Cyberpunk, what you're seeing, and this is running on my friend's machine in Sharjah, which is around 20 kilometers away from my house, approximately. And we had a latency of, I think, between 5 to 7 milliseconds. I was using something called Barrier KVM. You can use Barrier to remotely, you can use your keyboard and mouse to remotely connect to other machines using Barrier. We were using IPv6 because we don't have to worry about NATs anymore. So I could remotely connect my keyboard and mouse to his machine. This is currently not running in a Docker container because we are still writing, or we're still building the implementation to execute games inside a Docker container. And kind of the challenges we face is how to run huge games, because you can't download it and install it and then run it. So we are still working on ideas around how to improve on that. But this is what we got running Cyberpunk on a peer-to-peer connection, which is pretty impressive in terms of the frame rates. And this is kind of me controlling his machine from my computer. So let's pause that. So this is, if you're interested on the project, you can join our Discord channel if you want to talk more about the projects and you have more ideas you want to provide to us. Check out our GitHub repository over here, where we have everything from installing. We have the entire documentation of how everything works. The slide just talks about the basic overview. The documentation gives a pretty in-depth understanding of how everything is done. And feel free to create a PR, or if you want to talk to me, you can email me at me@aquilon.io, or just create a PR or join Discord channel for your suggestions. And of course, as mentioned, to find out more about the projects, go to p2prc.aquilon.io to find more. So one more last thing I just did want to talk about is the paper we're writing on. This is where we use P2PRC to run TensorFlow tasks distributed. What you see here on your right side is a GPU, and then we have here, well, for example, we were able to do 71 images per second in processing. What we were able to do is, this is like generally how you run stuff, but using P2PRC, we were able to run this Horvath image across, say, 7-8 machines which had GPU access. And we were able to, so the TensorFlow script was the same script as how you run on a single machine. There was no change to that. But using there's an open source implementation called Horvath, which helps you run TensorFlow scripts distributed across multiple GPUs. So when you mean distributed, not just in your machine, but even GPUs which are outside, which are on other machines. And when combining with P2PRC, using that same script with one machine, 71.4 images per second, but we just had added like 4 GPUs, I think 3 to 4 GPUs, and it automatically increased up to 277 images per second. And this is almost a huge efficiency and saves you a lot of time in running heavily computed tasks by running anything distributed. This is just the last thing I wanted to show. So thank you for coming today, and I hope you enjoyed the talk.